Okay, so here I have a problem, and this is maybe a little bit different than the ones that would be in a textbook, but it's the electric field due to a charged rod. And I'm actually going to do this two ways. First, I'm going to use Python to solve it, and then I'm going to use calculus. And some people may do that the other way, but I think doing it with Python first kind of gives better insight into how this would work. So let me switch over to the paper, set it up, show you how we're going to do this, and then I'll switch over to Python. I'll build a Python program to find the electric field due to this charge rod, and then I'll go back to the paper and I'll do it with calculus. Okay, turn this off. I always say I'm going to turn this off, so if I don't really need to say that, do I? Okay, so here we have, let me move this. Here I have a charge rod right here, and it has a length of 0.1 meters, a total charge of 4 nanocoulombs. Wait, 4 times 10 to the negative 6. That's not nano. That's 10 to the negative. Let's put 4 times 10 to the negative ninth. And then I want to find the electric field over here at this point. And then I have the Coulomb constant, 1 over 4 pi epsilon naught. Some people write it as K. It's 9 times 10 to the ninth newtons meter squared per coulomb squared. So how do I find the electric field at that point due to this? Well, the first thing is if I have a charge right there, and it's not even at the origin, and I want to find the electric field right there, I'll call that R observation location. And I'll call this RQ for the location of the charge. The first thing I need to do is to find this vector, R. R is the vector from the charge to where I want to find the electric field. So this is just basic vector math here. And so I could say R is equal to the final position, R observation, minus RQ. And now once I do that, I can find the value of the electric field with this equation. E, as a vector, is 1 over 4 pi epsilon naught Q over the magnitude of R squared times R hat. That's the electric field due to a point charge at that observation location. Now, what if I don't have a point charge? What if I have a rod? Well, I can't do it, right? I can't do it unless I say, well, maybe it is a point charge. So if I take my rod and I break it into point charges, then I can find the electric field due to a finite number of point charges. So here's what I'm going to do. Let's take this and replace this with, let's say, 1, 2, 3, 4, 5 charges. So I'll say n equals 5. And if I do that, let me redraw a picture because I want to make sure that we can see this really well. So here's my rod, and it's actually 1, 2, 3, 4, 5, and then here's my observation location right there. So what I can do is I can find, let's label these 1, 2, 3, 4, 5. If I want to find the electric field due to this point right here, I could call that E1. And then I could find, E5. And then I could find E5, E4. I could find all these electric fields due to these things and add them up. So that E would be E1 plus E2 plus E3 plus E4. Why did I do 5? I should have done 4 plus E5. Okay, so I can do that, right? Because I can just use my value for my point charge. But I have to do a couple things. Number one, I need to find the vector location of each mass. Number two, I need to find the charge of each mass. So here's what I'm going to do. I'm going to do this in Python. So I'm going to first say dq. Actually, so let's just say, dq is going to be the total charge q divided by the number of pieces. And then I'm going to need this distance between one piece and the next piece. So let's call that dx. It's going to be L over n. And so really what I'm going to do is have a rod that looks like this. Here's my rod. I'm going to put a sphere right here at the origin, at the beginning of the rod. And then I'm going to find the location of the next charge, and I'm going to put it right here, a distance dx over. So when I get to over here, my final charge will be actually not quite at the end, and that's okay. But once I know the location of each of these charges, I can find the value of the electric field. So I'll say this, dE, this is my piece of electric field due to one of these charges, is going to be 1 over 4 pi epsilon naught dq over, let's call this r I, should we call that? Squared r hat I. That's an I. So if I pick once I know the location of each of these charges, I can find that vector r, and that's what I'm going to use to find this electric field. And then I just add them all up. Okay, so we're going to do this in Python. I think we're ready. And there's a couple tricks that we need to use. I'm gonna actually build this rod out of spheres. I'm going to use lists. So I'll put a link down below to my tutorial on lists, and hopefully you'll see as it goes. So let's just jump over there and start doing it and calculate the electric field. I'm going to display it too as a vector just for fun. Okay, so move my mic and switch to this. Okay, so I'm in Trinket. This is just one of my favorite ways of doing Python. Let's do charged rod example. Save it, and let's make this one bigger. Is that too? I think that's, is that what size is that? I think that's good. Okay, so let's just start entering in my values here. So the first thing I want to do is put in my value for k. K equals 9 times 10 to the 9th. Q, the big Q, I said was 4 times 10 to the negative 9th. And again, I'm not putting units in here because, I'm doing a numerical calculation. I actually have to have the numbers. L is 0.1, S is 0.2. Okay, so let's first calculate dq, and that's just going to be, I need n. N equals 5. dq equals q divided by n, and then dx is going to be L divided by n. And now let's put the observation location in here. So let's actually make it a sphere. Let's say OBS equals sphere, position equals vector. I wanted to put it at S, 0, 0. I need a size too. I want to make it kind of small. I don't want it to stick out. So let's say radius is equal to, let's say 0.1, let's say 0.01. I don't know, that's fine. Now I'm going to make my spheres. Let's say this. I'm going to say QS is my list of spheres, and it's empty. And I'm going to have a temporary location that I can move around. So let's say temp R equals vector 0, 0, 0. That's the end of the rod. That's the left end. I'm going to put that end at the origin. Now I'm going to say while temp R dot X is less than L, do the following. So this is going to go through different values of temp R and build a rod. Okay, so let's say QS equals QS. And there is this append function that you can do. I just like adding it on this way. I want to add a sphere. The position of that sphere is going to be equal to temp R. The radius of the sphere is, let's say, 0.01. I made that the same size. Let's make this smaller. Okay. Now I need to move my x value, so I'm going to say temp R equals temp R plus the vector dx00. 0. So what that will do is I'll move over to the next position, and then once I'm done with up to the value L, I should have 5 spheres. Let's see, let's save this and let's run it and see if it makes my rod. Okay, so there you go. So 1, 2, 3, 4, 5. So that looks pretty good, and there's my observation location right there. So I have my rod, and each one of those I know the charge, I know the location, and we're all good to go. So now let's calculate. I could probably do it in here. Yeah, let's just do it all together. So I'm going to say E equals vector 0, 0, 0. So this is going to be, what I'm going to do is calculate the electric field due to each of these pieces at the observation location, and then add it to this vector, right? So what I'm going to do is I'm summing up all these things. And that's a key. We're summing up small electric fields. So let's calculate DE. DE is going to be equal to, remember, I'm already at one of the charges. Oh, I need to do it right up here. I need to do it before I move this. So I can say DE equals K times DQ times, now I need to find this vector. Let's call this R equals R obs.pos minus temp R. So what this temp R is the location of the charge. I just made it, I just put it in there. obs.pos is the vector value for the observation location. So R is a vector from the charge I'm on to the observation location. So now I can just multiply this by norm R. That's the unit vector R hat in the direction of the vector R. And then divide this by mag R squared. Then I can add that, say E equals E plus DE. So I'm calculating the electric field due to each little piece, and then I'm adding it to the other piece, to the total electric field. And then down here, I'm just moving to the next position. And that should be it. Then I can print E equals, yeah, I'd put that in there, E newtons per coulomb. Let's run it, save it. Okay, so there it is. And let's go ahead and draw it too. E arrow equals arrow, position equals obs.pos, and then the axis is going to be equal to E, and the color equals color.yellow. And there's going to be an error here, but I'm doing it anyway because I want to show you. So there's my arrow, and you see that I have, the problem is that I had my length of my rod was 10 centimeters, and the value of my electric field is 1,550 newtons per coulomb. So I've displayed this as a length arrow, right? Because it's an actual physical arrow. So that's too big. So I can do this. E scale equals, let's say, 1e negative 5. I'm just guessing there. You can guess. And then I'm going to go over here and say the axis is E scale times E. So this will make that arrow smaller. That's a little bit too small. Let's make that 3. Okay, so there you go. Now I can increase this to, what if I increase this to 15 pieces? See, it still works, right? And actually get a stronger value of the electric field. It went up. Let's 17, 12. Let's see if I keep increasing it to 20. See, now it's not increasing that much anymore. So I could keep increasing, I'd get better answers, but at some point I really don't get that much of a different an answer. And this would be a great thing to do, is to plot the value of that electric field as a function of the number of pieces that you break it into. That would be fun. Okay, now I do want to show you this. What? This is the awesome part. What if I move this observation location up here? Well, nothing changes, right? I can just, let's just put this at SS0 and rerun it. See, there's my electric field. It still works. It still works. And this is something that is not trivial to do using calculus, is to find the vector value of the electric field at some other arbitrary location. That's not so easy. Now, what I want to do is, how do I know that the expression is the same? I'd really like to make a graph of the electric field as a function of distance from here. But let's go jump over to the calculus way, and then I'll come back over here and I'll do that so that I can make a plot. I want to make a plot of the electric field as a function of distance for both of these two methods. And that's what I'm going to do. Okay, so but I want to do this with calculus. So let's switch back over to the paper, just like I said, and we'll do it over there. And then I'll come back. Paper. Move my mic. Okay, I'm going to start a fresh sheet of paper. So here is my rod. and then here's my observation location right there. And so this is the distance S, and then I break this into a tiny piece of the rod, and I'll call that a length dx. And it has a location of x. And so what I'm going to do is add up all the pieces from x equals 0 to x equals L. Okay, so the first thing I need to do is to find the electric field here, dE. Now, this is a vector, but all these pieces are pointing in the same direction, so I think it should be clear that I can just add up and find the x components of the electric field. So I can say dEx is going to be 1 over 4 pi epsilon naught dq, right? That's going to be the charge right there, divided by this. I'll just call this as r squared. And I don't have to write a vector because I've already said it's in the x direction, so I'm cool with that. This seems tilted. Okay. Now the first thing I need to do is get a value for dq, because I need to get dq and r in terms of the variable x, because x is the thing that's going to be moving, right? So let's say that if this rod has a uniform charge density, then the total charge q divided by its length should be the same charge of the piece divided by its length. So that charge is dq, and it has a length dx. So if I solve this for dq, I get dq equals q over L dx. And I can put that in right there. And then I'll get my integration variable dx instead of dq. So that's good. Now what about r? If this is the distance s and this is the distance x, then this distance r would be s minus x. So if I put that in, I get dEx equals 1 over 4 pi epsilon naught. dq is going to be q over L dx. And then I get s minus x quantity squared. So that's my electric field due to one small piece in here. Now I just need to add up all the pieces, and since I want to take the limit as the piece size goes to 0 and the numbers goes to infinity, and that makes it an integral. So I can say Ex equals the integral 1 over 4 pi epsilon naught q over L from 0 to L dx over s minus x quantity squared. You could just look this up in an integral table, but it's not that hard to do, because if I let u equals s minus x, then du is going to be the derivative of s is 0 since it's a constant, so I get the derivative of negative x, which is negative dx. So this becomes the integral 1 over 4 pi epsilon naught q over L. I'm going to leave my limits from x equals 0 to x equals L of negative du over u squared. Now that I can integrate, right? So that's just going to be the power, using the power rule, I get negative, which is already negative sign there. So I get 1 over 4 pi epsilon naught. I get 1 over u. But I'm going to put my u back in there. Q over L 1 over s minus x from 0 to L. And this is going to be equal to 1 over 4 pi epsilon naught q over L. And then I'm going to get 1 over s minus L minus 1 over s. Right, because when I put in 0, I get just s. Okay, so then we can simplify this a little bit. If I get a common denominator of s minus L times s, then I multiply this one by s over s, and this one over s minus L over s minus L. But then I'm going to get this. I feel like I'm 1 over 4 pi epsilon naught q. Oh, I should just do this piece of paper. I'm squishing it in. I tell my students, don't squish it in. You got plenty of room. Why? You got plenty of paper. Just use more paper. So I have 1 over, let's write it, Ex 1 over 4 pi epsilon naught q over L. Then I have s over s minus L times s minus S minus L over S times S minus L. See, I got a common denominator. You don't have to do this, but it's useful. So this is going to be equal to 1 over 4 pi epsilon naught Q over L. S minus, now I have a minus S and then a plus L. All of that over L. No, it's S minus L times S. And these cancel. And then I have L over this, but then there's an L right there. So now I get 1 over 4 pi epsilon naught Q over S minus L times S. And that's EX. Now notice that it has the same units as the electric field due to a point charge, which is charge over distance squared, and this constant over here, so that's good. Also notice that if I let L go to 0, then I get Q over S squared. That's the electric field due to a point charge, so that makes sense. So this is pretty good. Okay, so now what I want to do is to make a plot. I can put in my value for S, right? I can put in S equals 0.1, and I'm going to do that. That's the first thing I'm going to do, and get EX and compare that with my program. That's good enough, but I want to make this graph, okay? So that means I have to rerun my whole program before a whole bunch of different times. So I want to make a graph of the electric field as a function of X from, let's say from 0.15 to 2.25. And so I'll just break that into a whole bunch of pieces. I'll use this to plot it, and then I'll do it the other way to plot it too. So let's go back to Python. Where'd my mouse go? There it is. Let's see. Computer. There we go. Hello, computer. Okay, the very first thing I'm going to do is just come down here and do what I call eCalc. eCalc is, I'm just going to put in my expression and use the value of S. And that way I can just make a comparison. Let's say it was K times Q, I'm looking over here, divided by S times S minus L. I think that's right. Yeah. And let's print that. Print eCalc. The theoretical is eCalc newtons per coulomb. Oh, you got to put a space there. Okay, let's run that. Oops, get that paper off. I got a lot of paper. Okay, so you see there, we don't have the same thing, but it's pretty close. And I bet if I change this to 50, it's getting closer. Okay, I want it to be the same. Let's do 80, 800. I could do 800. Huh. Let's do 200. Okay, it's getting really close. I think the issue here is that this electric field right there, it's because I put my charges to the left side. So it really does make a big difference between this little charge right here on the end is a little bit further away than the actual charges. And that's why I'm getting a difference, but that's pretty close. Okay. And I'm pretty happy with that. Switch it back to 200 because I don't want it to be exactly the same. I want to make it different. Okay, so let's make a graph. The first part, so I'm going to come up here. Let's just go T graph equals object graph. Is this taking too long? That's okay. And the X title, let's see. Let's just say the title equals EX. That's fine. Due to rod. X title, got to spell it right. Title equals X in meters. And then the Y title is going to be equal to EX in newtons per coulomb. Okay, FC is going to be G curve. So FC is going to be my theoretical calculate, my calculated electric field. So it's going to be G curve is a built-in function in Python. I want to make this the color blue. And then my observation location is right there. I can actually move that. Let's do, trying to decide here. Okay, let's say x temp, x start is 0.15. And then dx, I already have that. So let's say dx temp. It's going to be, this is how many pieces I want to break it into. So let's say 0.01. Yeah. Okay, so now while xt is less than or equal to 0.25, let's see. I already have it down here. Let's just copy that. This is the theoretical electric field, and then I'm going to plot that. So fc.plot x e calc, and then I'm going to increase x temp. Oh, you know what? Okay, x temp plus dx temp. So this I need to change to x temp. This is my location. This is different from the x before. And this is xt. Okay, I think that works. That should make a graph of the electric field as a function of distance. Yes, there we go. That's my electric field as a function of distance from the rod. That's the theoretical calculation. Okay, now I'm going to make another graph. And it's a little, I think maybe my dx is too, let's make this 0, 5, make it smoother. Okay. Now let's make another curve. FP for Python. G curve. Color equals color.red. And let's give it a label. Numerical. This is theoretical label. Okay, so now down here, I'm actually going to move my thing, but let's just say, let's define this as a function. Def enum. And in that, I'm going to, let's just get past it the vector position r. No, s. S vector. So I can say s vec. I know I'm doing this terribly. And then, so what this is going to do, calculate the electric field due to the rod by breaking it into pieces. I guess I should give it in too. In. Okay, so now I'm going to put all this stuff in. Then I'm going to move my observation location. And it's going to be SV. SV is, let's call it SX. Because that's the only thing I'm going to move. So let's put this at SX. This is going to be temp over. That's fine. That's fine. That's fine. I need X in there. Because I put it up outside there. So actually, dq equals q divided by n. Yes, I'm using global variables. That's bad. dx equals L divided by n. So I can get rid of these up here. I guess there too. That's fine. That's fine. X equals 0. I don't have that. So X. No, temp. I did. I got a temper. That's fine. I'm making this way more hard, maybe more complicated than it needs to be. Okay, so that's fine. R. I think that's fine. I think that's all good. And then instead of printing, and I'm not going to make the arrow, instead of printing, I'm going to return E. Yeah. And let's just get rid of these things. And let's just test it. So let's say print enum sx is, let's see, 0.2, 20. And let's see if it returns a value or if it gives me an error. Okay, yeah, so it's working. Great. Okay, so now up here, let's just go down and do the same thing again. I'm going to print out I'm going to go up here, and I'm going to say, again, xt equals 0.15, dxt, I'm resetting these, 0, actually I could just do this. Let's just copy this, cut that, and put it down here. I think, I'm not sure if I have to have that before or after the thing, but I'm going to calculate, I'm going to plot two things. Let's say what do I call it? fp.plot xt, and then I'm going to call my function enum of the value, my x value is going to be xt, and then let's say I'm going to use 20 data points. And then that should work. If this works, I'm going to be really impressed with myself because I'm just, aha, it didn't work. Oh, that's right, I can't plot a vector. So this returns the vector location, so I just need the x component, so I'll say dot x. Look at that. What the heck, it worked. I can't believe it. But you can see here that they don't quite agree, but the further away they get, the better, because it still has the same amount of charge. Now, if I have different pieces at different locations, it's really not that big of a deal. I can go down here and change this to, 40, and those two curves should get closer together. See? There you go. Okay, there you go. I calculated the electric field due to a rod. I did it two different ways. I showed that they agree, and I'm pretty happy with this whole thing. So I'm going to put some links down below. I'm going to give you the link to this code and a couple other things that I could think of. But hopefully you enjoyed this. I had a good time. I'll talk to you guys later.